Databases and caching layers use Bloom filters to quickly reject lookups for non-existent keys without hitting disk or network. It's a probabilistic data structure, small, fast, and sometimes wrong, but only in one direction. Today we'll build one in Java, understand the math behind optimal sizing, and see it in action. All in about 160 lines. All non-inserted words correctly return false, no false positives in this run because the filter is lightly loaded. If we inserted many more elements, false positives would start appearing, exactly as designed. You've built a Bloom filter from scratch, the same data structure that Google Bigtable and Apache Cassandra use to avoid expensive disk seeks. These two methods implement the well-known formulas. Optimal bit size computes m, size, from n, expected insertions, and p, false positive rate. Optimal hash count gives k, number of hash functions, from m and n. They guarantee the filter meets the requested false positive probability as long as you don't exceed the expected insertions. Add first calls hash, element, to generate k different hash values. For each hash, it sets the corresponding bit in the bit set, modulo size to fit. We use Math.abs because hash values can be negative. The insertion counter is increment for stats. mightContain computes the same hashes. If any bit is 0, the element was never added, return false. If all bits are set, it might have been added, we return true. This is the core property, no false negatives, but possible false positives. We generate k hashes from two independent hash functions using a technique called double hashing. First we compute two base hashes, h1 from MD5, h2 from SHA-1. Then the ith hash is h1 This gives us effectively k independent hashes without needing k different hash algorithms. For production, one would use a faster library like Guava's Murmur 3, but this demonstrates the principle. We use java.security.messageDigest for the hashes. MD5 hash returns an int from the first 4 bytes of the MD5 digest, SHA-1 hash does the same from an offset, to make them different. Byte array to int converts a slice of a byte array into an integer via bit shifting. These are simple implementations, they work well enough for demonstration. Small getters expose the filter's parameters and current state, useful for monitoring and debugging. We create a Bloom filter expecting up to 1000 elements with a 1% false positive rate. The console prints the calculated bit size and number of hash functions, showing how the math works in practice. We add 7 fruit names and then check each one. All should return true, the filter never produces false negatives. We test 5 words that were never added. Most should return false, but due to the probabilistic nature, 1 or 2 might incorrectly return true, false positive. The odds are low because we inserted only 7 elements, far below the expected 1000. All non-inserted words correctly return false. No false positives in this run because the filter is lightly loaded. If we inserted many more elements, false positives would start appearing, exactly as designed. You've built a Bloom filter from scratch, the same data structure that Google Bigtable and Apache Cassandra use to avoid expensive disk seeks.